In a multi-programming system, processes request resources. If these resources are being used by other processes, then the process enters a waiting state. However, if other processes are also in a waiting state, we have deadlock. For example, suppose that process 1, P1, requests a printer. We show the process with a circle and it requests the resource printer. Because it is free, it is allocated to process P1. We are showing this situation with an arrow from the resource to the process. Then process 2 requests the tape unit and gets it. So we have an arrow from the resource tape to the process P2. Then process P1 requests the tape unit, but because it is allocated to process P2, it waits here. This request is not satisfied. It is requesting and waiting for it. And then process 2 requests the printer. This is the process 2 requesting the printer. Because it is already allocated to process P1, process 2 should wait for it. These resources can be used by a single process at a time. Process 1 and process 2 are deadlocked. They are waiting for each other. In this chapter, we shall analyze deadlocks with the following assumptions. A process must request a resource before using it. It must release the resource after using it. The sequence is request, use, and then release. A process cannot request a number more than the total number of resources available in the system. If the resource is not available when it is requested, the requesting process is forced to wait. In some operating systems, the process is automatically blocked when a resource request fails and awakened when it becomes available. In other systems, the requests fail with an error code, and it is up to the calling process to wait a little and try again. The exact nature of requesting a resource is highly system dependent. In some systems, a request system call is provided to allow processes to explicitly ask for resources. In others, the only resources that the operating system knows about are special files that only one process can open at a time. These are opened by the usual open call. Here, an example of using a semaphore to protect resources is given. In part A, we have one resource, and in part B, we have two resources. This is the case. We have one resource. The first semaphore type is defined, then the integer semaphore resource one is defined here, and the code is as follows. Void, there is no return value from the process. The name of the process is process A. There is no parameter. Done on the semaphore resource one. Here the address is sent. Use resource one, and then up resource 1. First request the resource, when get it, use it, and then release it. Here we have the case two resources. Again, there is type definition for integer semaphore, and semaphore resource 1 and semaphore resource 2 are declared here. Here is the process A, which is going to use these two resources. Done resource 1, done resource 2. Use both resources, and then up resource 2 and up resource 1. Here first they are requested by the down operation, and then they are used and both are released by the up operation. Here first they are requested by the down operation. After both are used, they are released. Here we have two processes using two resources. Part A is a deadlock-free code. Here we have declaration of the semaphores, resource 1 and resource 2. Process A has done resource 1, done resource 2, use both resources, and then up resource 2 and resource 1. And the process B has the same code. Notice that resource 1 and resource 2 are requested in the same order in both processes. In part B, we have a code with a potential deadlock. Here again we have semaphore declarations, resource 1 and resource 2. The code for process A is the same as the one given in part A. However, for process B, the order of the request of the resources is just reversed. First, resource 2 is requested. We have a down operation on resource 2. Then resource 1 is requested. We have a down operation on resource 1. And if the request order is just as given in the previous example on tape and printer, and the execution of the code, if the concurrent execution of the processes A and B goes such that down resource 1 by process A, then down resource 2 by process B, and then down by process A on resource 2, and then down by process B on resource 1. This is resulting in a deadlock, as we have seen in the example related to printer and tape previously. The formal definition of deadlock is as follows. Definition: a set of processes is in a deadlock state if every process in the set is waiting for an event, release. That event can only be caused by some other process in the same set. For this model, we assume that processes are single-threaded, and we assume that no interrupts are possible to wake up a blocked process. A deadlock occurs if and only if the following 4 conditions hold in a system simultaneously. 1. Mutual exclusion. 2. Hold and wait. 3. No preemption. 4. Circular wait. For mutual exclusion, at least one of the resources is non-shareable. Each resource is either available or assigned to exactly one process. If it is requested by a process while it is being used by another one, the requesting process has to wait until the resource is released. The second condition, hold and wait. Processes currently holding resources that were granted earlier can request new resources. There should be at least one process that is holding at least one resource and waiting for other resources that are being held by other processes. The third condition is no preemption. No resource can be preempted before the holding process completes its task with that resource. Resources must be explicitly released by the process holding them. The fourth condition is circular wait. There exists a set of processes P1, P2 up to Pn such that P1 is waiting for a resource held by P2. P2 is waiting for a resource held by P3, and this is going on similarly for the other processes up to Pn-1. Pn-1 is waiting for a resource held by Pn, and then Pn, this process, is waiting for a resource held by P1. There must be a circular list of 2 or more processes, each of which is waiting for a resource held by the next member of the chain. Resource allocation graphs are drawn in order to see the allocation relations of processes and resources easily. In these graphs, processes are represented by circles and resources are represented by boxes. Resource boxes have some number of dots inside, indicating available number of that resource, that is, number of instances. Here we have an arrow from P1 to resource. That means that process P1 is waiting for resource Rj. Suppose that this is resource Rj. And this one is showing that resource Rj has been allocated to process P1. Here there's an arrow. Here there's an arrow from the resource to the process. So this is showing holding a resource, and this is showing requesting a resource. And this is showing the case there is a deadlock. Here notice that there is a cycle on the graph. If the resource allocation graph contains no cycles, then there is no deadlock in the system at that instance. If the resource allocation graph contains a cycle, then a deadlock may exist. If there is a cycle and the cycle involves only resources which have a single instance, then a deadlock has occurred. However, if there is a cycle, but the cycle involves some resources having more than one instance, then a deadlock may occur or not. Here we have process P1, P2, and P3. We have resources R1, R2, and R3. Notice that R2 has two instances. One is assigned to process P1, the other one is assigned to process P2, and process P3 is waiting for the resource R2. And meanwhile, P1 is requesting R1, which is held by P2, and P2 is waiting for the resource R3, which is assigned to process 3. Here in the graph, we have two cycles. One is this cycle, and the other one is this big cycle. In fact, P1, P2, and P3 are deadlocked because process P2 cannot continue because it is waiting for R3, which is assigned to P3, but it is waiting for R2. We have two instances of the resource, but they are allocated to processes, and P1 is not able to continue, P2 is not able to continue, so none of the processes are able to continue. There's a deadlock in the system. This is another example. Here we have four processes, P1, P2, P3, and P4, and two resources, R1 having two instances, and R2 also having two instances. There is a cycle here, but there is no deadlock because P2 and P4 can terminate. They are not waiting for any other resources. So P2 can terminate, for example, and one of the instances of R1 releases, and it can be assigned to process P1, then the cycle is removed here. Then process P1 or P4 can terminate, and after that, process P3 can terminate when one of the instances of resource R2 becomes free. Or first P4 terminates, and then one becomes free, then P3 or P2 can terminate, and after one of the resource becomes free here, then P1 can terminate. Here an example of how deadlocks occurs and how it can be avoided is shown. We have three processes in the system. Process A requests R and S, then use it, then release these resources. Process B requests S and T. After using them, it releases these resources. And process C requests T and R, and similarly, it releases these resources after using it. If the execution order is such that A requests R and gets it, B requests S and gets it, and C requests T and gets it, and continue here. A requests S is assigned to B, so A should wait. B requests T, but it is assigned to process C, it should wait. And C requests R, and it waits. And notice that there is a cycle in the system now, and the system is deadlocked because there is a cycle and all of the resources are single instance. Here the order of the requests are changed. First A requests R and it is assigned. C requests T and it is assigned. And before B requests S, A requests S, it is given to process A. Then C requests R, C requests R, A releases R, A releases S, and then there is no deadlock in the system. If later B requests the resources, it will able to use them. Strategies are used for dealing with deadlocks. The first one is prevention. This is by structurally negating one of the 4 required conditions. The second one is dynamic avoidance by careful resource allocation. However, avoidance is requesting how many resources at most is going to be used by each process. The third one is detection and recovery. Let deadlocks occur and then detect them and take action. The fourth one is ignore the problem, maybe it will go away. And this is not a good solution, of course. This is called Ostrich algorithm. Methods for handling deadlocks are as follows. The first one is deadlock prevention. It is preventing deadlocks by constraining how requests for resources can be made in the system and how they are handled by the system design. The goal is to ensure that at least one of the necessary conditions for deadlock can never hold. Deadlock avoidance. The system dynamically considers every request and decides whether it is safe to grant it at this point. The system requires additional a priori information regarding the overall potential use of each resource for each process. This allows more concurrency. The third one is deadlock detection and recovery. Deadlock prevention. Assure that at least one of the conditions is never satisfied. For example, mutual exclusion may be omitted if possible, or hold and wait, or no preemption conditions can be omitted, or circular wait. To prevent the system from deadlocks, one of the 4 discussed conditions that may create a deadlock should be discarded. The method for preventing those conditions to hold are as follows. Mutual exclusion. In general, we do not have systems with all resources being shareable. Some resources, such as printers, may be non-shareable. So it may not be possible to prevent deadlocks by denying mutual exclusion. Hold and wait. One protocol to ensure that hold and wait condition never occurs says each process must request and get all of its resources before it begins execution. Notice that this is getting all the resources at the beginning and not allowing any process to use it when this process is executed. Another protocol is each process can request resources only when it does not occupy any resource. So in this case, for example, the process may request 2 resources, and after using it, it releases them, and it may request other resources and use them. If it is not requested to use all these resources at the same time. The second protocol is better. However, both protocols cause low resource utilization and starvation. Many resources are allocated, but most of them are unused for a long period of time. A process that requests several commonly used resources causes many others to wait indefinitely. Now let's consider no preemption. One protocol is if a process that is holding some resources requests another resource and that resource cannot be allocated to it, then it must release all resources that are currently allocated to it. Another protocol is when a process requests some resources, if they are available, allocate them. If a resource it requested is not available, then check whether it is being used or it is allocated to some other process waiting for other resources. If it is used, the requesting process must wait. If not, then the operating system preempts it from the waiting process and allocates it to the requesting process. This protocol can be applied to resources whose states can easily be saved and restored. For example, for registers and memory space, but it is not good for the printer, for example. The last one is related circular weight condition. If circular weight is overcome, then deadlock will be prevented. One protocol is to ensure that circular weight condition never holds is impose a linear ordering of all resource types, then each process can only request resources in an increasing order of priority. For example, set priorities for R1 S1, R2 S2, R3 S3, and R4 S4. With these priorities, if process P wants to use R1 and R3, it should first request R1, then R3. Another protocol is whenever a process requests a resource Rj, it must have released all resources Rk with priority Rk greater or equal to priority of Rj. Again, this is preventing circular weight. Here is the summary of approaches to deadlock prevention. We have 4 conditions, and the approach for discarding the corresponding condition are summarized here. For mutual exclusion, approach is spool everything, which is not possible for some resources. Hold and wait, request all resources initially. No preemption, take resources back. Circular wait, order resources numerically.